From chaos to order, unleash the power of Gram-Schmidt orthogonalization. Get started on the right bases. I'm excited to introduce a new playlist covering the appendix of this book, as linear algebra is a fundamental topic in the scientific community. If that interests you, be sure to hit the subscribe button for more. Now let's see what we're dealing with today. In today's problem, A.4, suppose you start out with the bases e1, e2 up to en that is not orthonormal, meaning that they're not orthogonal, i.e. perpendicular, and they're not normalized, i.e. that they have a length of 1. The Gram-Schmidt procedure is a systematic ritual, that's a really good way of putting it, it's a ritual, for generating from it an orthonormal bases e1 prime, e2 prime, en prime. It goes like this. Stop 1, normalize the first bases vector by dividing by its norm. So we have some vector e1 prime equals the given vector, and then divide it by its magnitude called the norm. So we're just getting rid of its length, so to speak. And then part 2, find the projection of the second vector along the first and subtract it off. And if you remember, the projection operator from the quantum mechanics book looked like E1 with the outer product E1 here, and then E2 was the projection onto that. This vector is orthogonal to E1 prime, and then normalize it to get E2 prime. Let's take a quicker look at this. So given that I have vector V1 and V2 here, what I can do is go ahead and normalize V1. So I take the first vector, normalize it to make it into E1. What that does is, as you see, we keep the direction that it is, but we shrink its length. Then from there, we look at this V2. We see that V2, this arrow here, casts a shadow down onto V1. And that's where you see the dotted line here. This shadow down here is called the projection of U1, or of the projection of V2 onto U1. And if we get rid of this component, all we're left with is this vertical component, which is U2. From U2, we can normalize it to get E2. And then from there, you see that these two, E1 and E2, are now at 90 degrees to one another. And it didn't start that way. Clearly, V1 and V2 were not 90 degrees to one another, nor were they of normalized length, which is very important to quantum mechanics. And so we could repeat this for as many vectors as we have. Subtract E3, its projection along E1 and E2. Okay, subtract from that, okay. So we see E1, E3, E2, E3, prime, prime, of course, the new vectors, in the new vector direction, in the new vector direction. Get rid of them, and you're good to go. This is orthogonal to E1 prime and E2 prime. Normalize it to get E prime 3, the actual vector of interest, and so on. So use the Gram-Schmidt procedure to orthonormalize the three space bases E1 equals these components down here. Note that they're an 𝐻𝐾 component, so we're in Euclidean space, nothing too crazy. E2, another 𝐻𝐾, and E3, 0, 28, 0, so those zeros will help very much so later. Now, the Gram-Schmidt orthogonalization procedure is important because it allows us to transform a set of linearly independent vectors into an orthonormal basis, and we love that. I mean, look at 𝐻𝐾, they're orthonormal bases, but then the vectors we form from them, when we want to look at certain things with these particular vectors, which of course might be something like eigenvectors, or some other arbitrary vector, will be of importance to us later. Now, these are seen in several significant applications, quantum mechanics being the main one of interest. We see that the Gram-Schmidt procedure is used to create orthonormal wave functions, which are essential for describing quantum states accurately. And then another big one that I see in a lot of literature right now is data science. The procedure is valuable in data science and data analysis, and of course for the machine learning for feature selection and dimensionality reduction. Okay, so we'll see how these kind of play out together, but the concept here is that we can create the orthonormal bases from whatever arbitrary basis, so long as they're, or arbitrary vectors, so long as they're independent, okay? So that's what we have to deal with. Now let's get started into how to actually solve this without me rambling for 3 hours. So part one, let's go ahead and summarize the three space bases vectors in column form instead of the unit vector form for the ijk. Recall then, the E1 they give us was 1 plus I in the first component, 1 in the second, I in the third, so I hat, j hat, k hat. Redo this for all the other ones, and we'll color code them to make it easy to see and follow along. Now from here, the first step that we had to do was to normalize the first basis vector. To do this, we have to call upon our friend A.25, which is the inner product of this. Now the inner product tells you that this is the magnitude of the vector itself. Okay, well, kind of. It's the projection of the vector onto itself. And so this is squaring everything, so to speak. But by, quote, squaring it, we get a positive number. So we see that we get each component in the magnitude squared. The magnitude, though, because of the complex numbers, means that we have to take the conjugate on one side, multiply it by the thing itself. So once we do that, we see we get a negative I here and a negative I here. And then we can simplify this because after distributing one into both of those, I into both of those, this I and this I will cancel in the cross terms, leaving you with the negative I here times I there, so negative I squared equals 1. So we get the 1 here, 1 from these two terms, and then that turns to positive 1 as well. So we're saying that this is 4. Now, because in essence this is squaring the vector, we also have to find its magnitude by taking the square root, which we'll do in just a second. The other way to find this inner product instead of using component-wise magnitudes is to use the transpose conjugate method. And this is what we see more or less in the quantum mechanics literature and things like that, where we're taking a vector and we just use a dagger operator, which transposes it, so we go from column to row, and then we take the conjugate. What that does for us is it allows us to take the inner product by the definition's sake of two vectors being dotted with one another. So this tells us row to column, that multiplication happens, and we get the exact same thing we had last time, so we know that that equals 4. That being said, this whole squaring thing, because as you see I'm multiplying the vector by itself in some way, the square needs to be undone. And that's where equation 8.22 comes in and tells us that the norm of this is the square root of the inner product, which is the, quote, squaring of everything. As a result, taking the square root of 4 gives us 2. Not too bad. So from this, we create the new basis vector, the prime vector, which is just the vector given divided by its magnitude or norm. So that's where the 1/2 comes from. And then this is the vector given. Or if we want to write it in component form, since that's what was given to us, we can do that as well. Now the next two parts are going to be a little clunky because we have to find projections and minusing them. So let's get to it, and just bear in mind that this is going to be a little tedious. Okay, so the projection of the second vector onto the new vector tells us that we need to take the inner product with the new vector and the E2 vector. So using the conjugate transpose method or the dagger, we see here that this 1/2 just plays out front, no big deal. And then we get the transpose conjugate here. So now we can go ahead and take the dot product accordingly, dimensionally, row to column, we're good to go. So first component to I, second component to 3, last component to 1. We see it all there. Distribute and simplify. So again, negative I squareds are positive 1. The i's just get annoying after a while, so be very careful with that. And then we see that we get 1/2, 1 plus 3, and we're good to go because this negative and this negative cancel in the cross terms, so we're good to go. So eventually, we see that we get 2 here from that inner product. And now if we define gamma, because again, we're not normalized, so we're not going to define it as a new vector yet. If we define gamma as the basis vector minus the overlap here, which is the projection given onto the vector itself of interest, if we minus that off, then we see by just row vector or column vector manipulation, the 2 and 2 here cancel. So we see that that goes away. And now if we take the difference after those constants cancel, if we take the difference component-wise, again, we're in a vector space because we're a basis, so we know that this distributes and we have all the properties we like. So now that we see we can maneuver this negative sign to each component, 1 to 1 to 1, good to go. Distribute that into this parentheses. You see the I and I cancel, ultimately leaving us with -1, 2, and 1 minus I. Easy enough. Now we get to the other laborious part, which is combining 8.25 and 8.22, and we can just find the norm directly instead of having to take the inner product of the new vector in itself. We could just say, well, look, I'm just going to put the inner product inside the square root to start, save ourselves some algebra. And what that equated to in either direction was first component magnitude squared, second component magnitude squared, last component magnitude squared. Cleaning this up though, you know, -1 squared, 1, 2, 4. This one you have to be careful of because again you have 1 minus I times 1 plus I when you take the conjugate. Either way you get 2 out there, so you're fine. And then you add that together, that gives you 7 inside the square root. From there, now we can compose the new basis vector E2 prime, which is the gamma vector over the gamma norm, which is what we just calculated. So we're good to go here. Again, if you want to keep it in terms of the original basis vectors or the unit vectors, go ahead. I think keeping it in terms of the column vector is so much simpler once you already established that it's I, J, K, so you're in the Euclidean space. All right, last but not least, we have to now take two projections since we have two new vectors. So the projection of the third vector onto the new vectors gives us a, now instead of gamma, we're using xi, and we see that we have inner product here and a product here because we're trying to find the projection of E3 onto E1 and E3 onto E2 prime. So once we can subtract this off, we see that this first inner product, E1 prime E3, dagger of course, do the same thing we did last time. We see the multiplication because of these zeros goes by so much quicker. This term goes to 0, this term goes to 0, and so all we're left with is 28 inside. Beautiful. Divide that by 2, leaves you with 14. So much less painful with the zeros. Now, of course, we still have to have E2 prime with E3. Again, dagger, transpose conjugate. There's a negative though on that one. Or that should be positive, excuse me. That needs to go to positive. Let's see if I corrected it later. I guess I did not. Let me go ahead and correct that now then, if that's the case. It should be positive, and that should be positive. Either way though, because of the 0 that we see in this component in here, it goes away, so we're fine. This should be correct in the PDF though. Trying to transpose it to the PowerPoint just took a little while, but nonetheless, we're good to go. That being said, 56 over root 7, you may as well just keep it like that because when we add the vector sums together or the vector forms together, there's another root 7 there, so you don't have to rationalize it because that's just going to eat up time. And so now that we have these projections, scalar projections of course, we see that we have 14, which is the projection of E1 prime and E3, and then we have the E1 vector. So if I have just this, that's the scalar projection. If I have this thing together, this together gives you the vector projection, which is technically what you want. Again, this is kind of a quick intro in this appendix, but something that you need to use over and over again. So the bases that we want, minus off all the projections. This is that square root 7 I was telling you about. No need to rationalize this one because these two multiply together. So now all we need to do is see that this 1/2 reduces that 14 to a 7, and we can clean this up. All right, so first round of cleanup, 14 divided by 2 from that 1/2 gives you 7. Square root 7, that gives you 7. Now we can go ahead and distribute these into each component. Thank you, linearity, and all those nice aspects of the vector space. So 7 to each component, good to go. 56 divided by 8 or 56 divided by 7 gives you 8, as we see, 8 to every component. After we do that, distribute the 7, distribute the 8s. We see we get our new vectors here. After that, we need to go ahead and take these minus signs and apply them across every component. So first vector, second vector, third vector, all component-wise. Now we're good to go. Distribute the negative signs accordingly, cancel out signs accordingly. Once we do that, we get this. That can be simplified pretty quick. -7 is kind of on its own, so we're good there. -7 and +8 give you +1. All constants here, love that. And then we get negative 7i plus 8i, that gives you I here. Negative 8's by itself, easy enough. Of course, this just gives you the vector, we still have to find its magnitude, so let's get to it. So if we take the norm of this thing, or the magnitude, square root of the inner product, each component squared, we see that this leads to the 1 squared, then the 7 squared. Again, if you kind of realize that the conjugates purposely get rid of the cross terms when you're factoring out that modulus squared, you're good. 5 squared, 8 squared, and I squared, negative of course. Then we have, well, just add them together, and you get root 140. So that whenever you factor that out, because that's 4 times 35, you're good to go. Then this gives you the whole new vector, and we're perfectly fine. Take the 𝛏 vector, divide it by its magnitude, which is what we do here. Break it down into components if you'd like. Either way, you're good to go. And we see that we get our first, our last basis vectors. Now, to summarize this all, we see we get the complete set E1 through 3 prime of these new vectors. Now, for the patrons out there, I have done the checks on this on the orthonormal conditions, where I have checked both that their normalization, so they go to 1 when I take the dot product with 2 vectors, or the inner product with 2 vectors, and that I proved that they go to 0 when I take the inner product with E1 and E2, E1 and E3, and E2 and E3. So check that out on the Patreon. That is up for you, or will be by the time of this posting. Nonetheless, we get a full new set of vectors that are perfectly fine. Now, let's reinforce this concept with a picture. So this has nothing to do with our problem in terms of the actual vectors, but concept-wise it does, and I'll post a link in the description for you to go read up the article if you'd like. But here's a great illustration that someone made, where we have V1 going somewhere in the XY plane, V2 somewhere else in the XY plane. Again, we see that the angle between them is not 90 degrees. Then you have V3 coming outside the XY plane with some Z direction and also in some other direction out. Then after the procedure, we normalized V1 into E1, so we see how it got kind of shorter, but stayed in the same direction. Then E2, after subtracting off the projection, we now reorient it this way because of that subtraction and normalized it. We see that E1 and E2 create 90 degrees. And then we see E3, because V3 is the only one coming out of the plane, now points directly up with the normalization, and it's self-corrected by getting rid of the projections. And that is, especially if it's coming out the plane, it's definitely orthogonal to E2 and E1. So this is a pretty cool thing to have, especially if you're working in a crunch and a non-traditional vector set. Very, very important. That was a lot of fun and very important for several things. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I also just want to take a moment here to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together, we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.